Hi folks, come up with a great idea. I want to do a tutorial series on microcontrollers. Of course there are plenty other tutorials, so why do yet another one? Because pretty much anything I've seen so far is, okay, I'm going to do on a tutorial on microcontrollers. I'm going to use Atmel AVR. Or I'm going to use Microchip PIC, or I'm going to use TI-MSP430 or STM8 or whatever. And I think that's not exactly getting to the point. So what I'm going to do is I'm going to take Atmel AVR, Microchip PIC, TI-MSP430, and basically put them side by side and see where the differences and where the similarities are. And I've done that before with when I started to work with Unix a long time ago. Basically started collecting different Unixes that I hadn't worked with before, and it taught me a lot and gave me a much better understanding of what was going on and what options I have than just sticking with that one true religion that a lot of other people stick with once they've kind of mastered the first operating system or whatever, or programming language, or you name it. So this comparative approach basically means there's a good chance we'll get a much deeper understanding of the nature of microcontrollers than by just watching at a single one. It also gets us way more options when we do projects, because we can decide, okay, this project, it makes sense to use PIC for whatever reason, or to use an AVR, or to use an MSP430, or maybe even some others, because by the time we're through with at least 3 of them, the next one doesn't really worry us. Now, this has a couple of implications. First one is I'm not going to use the vendor or manufacturer supplied IDEs. If you want to, fine, no problem with me. But using 3 different IDEs at the same time is just asking for trouble. It just doesn't make sense. I'm going to use regular command line compilers, and in 2 out of 3 cases it'll be some variant of the GNU C compiler, GCC. I'm going to use, in this case, Linux. I'll explain later on why. But again, use whatever you are comfortable with. Another issue that I'm interested in, which is kind of related to this, but not quite, is actually portability. Now, microcontrollers, there's generally the assumption that you work with them, you first pick the microcontroller family, then do your stuff, and it's never going to work on anything else. And if you have to port things from AVR to PIC or whatever, you basically start from scratch. That's true if you do assembler, but the question is, how portable can we get things? It's obvious at some point we're pretty much at a point where trying to keep things even more portable will cost resources, which are by definition tight on microcontrollers. But the question is, how far can we actually get? I want to find out about that a bit. So this is kind of an experiment on my side. If you want to follow along, first thing you need is some sort of computer. And just because I've got a big fat, well, this is a more portable data center than anything else, big notebook workstation there, doesn't mean you need one. This is just because I need this to do desktop session recording. I'm not going to use that machine for anything else, actually. Or maybe some internet surfing to show you some kind of resources, but whatever. You also need to be familiar with C. Now, a couple of weeks ago, I've seen a posting in some forum, somebody saying, okay, I want to learn C and decided to do that on a microcontroller. Sure, why not? Go for it if you want to. If you want to, you can learn to ride a bicycle by putting a blindfold on, getting on your bike in downtown Bangkok during the rush hour on a motorway and try to learn it. but it doesn't make much sense. I mean, the usual thing when you learn to program C is for this 5-line thing doing hello world on standard output. Only on a microcontroller we don't have standard output. So if you want to do that on a microcontroller, we'd first have to come up with some hardware. We connect a microcontroller to some suitable display, then write the microcontroller equivalent of a device driver, and then send our hello world there. That's actually a project. So I assume that you're reasonably familiar with C, not with all the arcane features and weird preprocessor hacks or anything like that, but just some reasonably solid basic understanding to follow along. It's also helpful if you know a bit about Make. Now, I've been repeatedly charged and found guilty of dark makefile voodoo. Make is a strange little tool. It's annoying at times, but it's tremendously helpful and tremendously powerful, so we're going to use it. If you don't like it, if you don't want to use it, by all means use shell script or batch files in the Windows world, or use your IDE. Not my call. Whatever you feel like. But this is how I'm going to do it, because it makes things much more easily reproducible and to fixate things, so you can just make sure this thing is solved and I don't have to worry about it again. I just personally find it really annoying that on some IDEs you have to click 4 different places to get something done, and next time you change something in your program you start to click all over the place again. Not my way of working. I just want to tape make install, and that's it. Or maybe make test or whatever. This video will also address, or the series will address, a number of techniques and approaches to tackling new and complex topics, like working with microcontrollers, getting started with microcontrollers especially, or writing your first socket-based TCP IP client-server pair, which can be quite an experience, I can tell you from experience, or cooking your first 3-course dinner, if all your cooking experience so far is burning your coffee water. Pretty much the same always. So I'll talk about that, and I might actually do a video on this fundamental approaches things, where I use this as an example reference. Now, while I do things in parallel on 3 architectures, I've got a bit of a head start, so it might be reasonable for me, but not necessarily for you. You don't have to try all 3 of them at the same time. It's your call, really. Anyway, I mean, I'm not your teacher. I'm not going to give you a back grade, flunk you a test, or call your parents and complain about you. I assume you're grown up. For the purpose of this tutorial, doesn't mean you have to be of age or anything. Doesn't have to do anything at all with it. It just basically means you're capable to make your own decisions and live with the consequences. If you want to keep things easy, you're probably best off trying to find somebody you can ask questions when things don't necessarily work out the way you expect. I've been lucky enough to have a couple of people around, like the late Uli Graf, died a year and a half ago, a year ago, not even sure, or Peter Heimann here in Frankfurt, who actually came up with some tips, sent me going in the right direction, and that was quite helpful. If you don't have anybody like that, you can of course come to the forum at www.stepladder-it.com/bivblog/37 or wherever. But it's frequently helpful to have somebody to ask, somebody who takes a look at your PCB and says, there's a cold solder joint, I think, fix that first, when you're trying to fix a software problem. If you're on a tight budget, and pretty much anybody has started like that, I think, And I mean, I remember, being a high school student, going on a shopping spree with all my pocket money and buying 3 LEDs at once, plus series resistors, long time ago. But still, if you're on a tight budget, your best option is the TI launchpad. There are actually multiple launchpads these days. So this one is called the MSP-EXP430G2. Sets you back anything from 10 to 30 euros, so you want to shop around a bit. It's a very basic design. They basically left everything out that wasn't needed and made sure the rest worked. Very nice engineering, in my opinion. But otherwise, it's really your call, whatever you feel like. And yes, I'm going to use these at least to get started. Again, the way I do things doesn't have to be your things. I've got a bit of head start. I've got a slightly unusual background. There's a good chance that my C programming skills are above average and my electronic skills are below average compared to you, or the average of you, if you want. It's your call. Whatever you do, just face the consequences and try to learn from them. That's the whole thing, really. I just want to give you ideas, point you in interesting directions, and that's pretty much it. And if you have questions, if you think that I'm assuming things assuming you to be familiar with things that you aren't, or I do things in an awkward way that you have better ideas, let me know and just do what you want. And before we really get started and I tell you about what this is all about and how to approach it, one more thing we need to talk about, and that's Arduino. Now, Arduino was tremendously successful from the very day it was launched, and for good reason. I mean, they got a number of things really right. They've got an IDE that teaches pretty much every other IDE developer that yes, IDEs can be made this simple and easy to use. That was a slap in the face of pretty much everybody else, really. But I'm not going to talk much about Arduino. Why not? Because the exciting feature of Arduino is that it provides a pretty clean abstraction from the underlying hardware, the microcontroller. Very useful if you want to build a prototype and want to focus on your application, but not very helpful if you actually want to get down to the microcontroller. It's kind of like Java when it was first released. I mean, Java's got a bit old and crusty these days, but one of the fundamental ideas with Java was always that your application doesn't talk to the underlying operating system. You talk to the Java runtime environment, which is the same on all platforms, and the runtime environment ensures that it talks to the operating system, which provided you a much nicer abstraction layer, which was really helpful if you wanted to focus on your application, which also meant that you could actually port your application without changes from one platform to another. Really cool if you're focusing on applications. Pain in the ass if you wanted to talk to the operating system, you really had to, because Java at that point was pretty much hopeless. There were ways to do it, but they were basically meant to be painful. But not meant to be painful, but meant to encapsulate this underlying stuff best they can. And the Arduino is pretty much like Java. So you say, I want to talk to pin 13, which is up here somewhere, and I don't care which pin on which microcontroller it's connected to. I've got a bit of software code, a sketch, which runs through some sort of compiler which makes sure it compiles stuff in such a way that it works on the microcontroller on the target. Cool thing for some jobs, but not for what I'm interested in. Because What I'm interested in is actually talking to the underlying microcontrollers. It's basically really like talking C instead of Java in regular computer world. So, what are we going to do? I've drawn you a picture. Yeah, the whiteboard is back. And let me see that I can show you. This is basically what we're up to. So that is you or me talking to a computer using the KVM protocol, keyboard, video, mouse being optional, and use an editor to write some source code, which we run through a compiler to produce a binary image, which we run through some programmer software, which talks using USB or possibly RS-232, some programmer hardware, which connects to a target board using ICSP, JTAG, and whatever variants like ISP, SPI-by-wire, BSL, whatever. And more specifically talk to the microcontroller, the MCU, microcontroller unit, on the target board to install the software there, and the microcontroller then talks electrically to some sort of peripherals like the archetypical LED, which then produces visible light, which tells you everything works. Now, if you try to set this up like this, you'll never make it. It doesn't work, if only because to write the source code you need to know what the target board looks like. So you might say, okay, I'm going to build the target board first and then work backwards. Doesn't work either. The way for this to work is to focus on things strictly necessary and to simplify or eliminate things that aren't strictly necessary at the certain step you're trying to do. And this is a schematic. So another good trick is to see how does it scale, because it doesn't. Building a target board, writing the source code for it is the real deal. Installing a compiler and a programmer hardware, programmer software is not such a big deal. So what can we do? First, we take a target board off the shelf. For pretty much all microcontrollers, you get some sort of development and test and whatever boards you can start with. Much simpler than building this, not knowing if it works, and then trying to get all the rest set up and then trying to start and troubleshoot things. So we take target boards off the shelf. Don't have to be expensive. Already mentioned the TI Launchpad. Talk about the other ones later on. Programmer hardware, we're going to use off the shelf as well. There's a long-standing tradition of building these yourself, which comes from an era where these were hideously expensive. We can still spend more than 1,600 euros or so for some of these, but you don't need those. You can get away with something like 10 euros or 15 or so. Programmer software is off the shelf again. Computers, nothing fancy. And what we're going to do, we're going to skip the source code compiler stuff. We're just going to take binary images from this newfangled thing, what's it called? Internet. That's a word. I think. Basically means you will find tarballs on the web forum, on the forum for the BIVBlog. So it's www.stepladder-it.com/BIVBlogs/37. You'll find two tarballs there by the time you watch this. One is binaries, which include binary images, so you don't have to worry about compilers and anything. Just make sure that this part works. And then, of course, there's sources, so you can see that the compiler works and start modifying it into your own source code. And with that approach, things are fairly simple and straightforward. The next couple episodes will deal with programmer software, programmer hardware, target board for the three architectures I'm going to use. And one more thing left to do while we're at it, set up the computer. And there's something about that. I've got the big fancy mobile data center here for the desktop recording only. The computer I'm actually using is, probably guessed it, Raspberry Pi version 2, and that's actually one of the reasons why I use it. Well, first off, of course, I use it because it's good enough for the job. why use anything more expensive if we can get away with it? And I have one of these lying around. But there is another reason. The computer usually connects to the programmer using USB. And some of the programmers are just bare PCBs. You short the right pins at the wrong time, you can cause a short on the USB interface to the computer. And the USB specification doesn't require overcurrent protection on the computer side. Basically means things go wrong, you can really damage the USB interface on a computer. And it doesn't have to do with how expensive the computer is. The Toshiba Protégés, which I use a lot, because they're not as heavy and big and as expensive as this one, but still not exactly cheap machines, they don't have overcurrent protection. Raspberry Pi version 1 doesn't have overcurrent protection. Raspberry Pi version 2 has. And that's one of the key reasons why I use it. Now, if you use the Windows environment, or you don't want to use a Raspberry Pi because you don't have one, you just want to use your regular computer. Couple tips. First one, you don't need anything expensive, fancy, and powerful. Just use some old machine you have anyway. Second, protect the USB interface on your computer using an externally powered USB hub. Saves a lot of trouble. It's widely considered good practice, especially so if you build microcontroller boards with a USB interface back to the computer. Not the programmer, but also on the target board. And finally, it's better to use a desktop computer than a notebook, because if you damage the USB interface on a notebook, it's frequently impossible to get repaired, whereas on a desktop PC, you just put in a USB card in an empty PCI Express slot, and you can continue to use the machine. Okay, so what do we need to do on our computer? Well, back to the picture. We need the computer. Yes, we need an operating system, obviously. We need an editor. In my case, that's Emacs, but if you prefer VI or whatever, your call. Not gonna start a discussion on that. We need a compiler. We need the programmer software. And now the Raspberry Pi has one disadvantage. It's not particularly fast. It's perfectly fine for programming microcontrollers, but when we play around with the Microchip PIC family, we actually have to build the compiler from scratch, and that takes about an hour and a half or so. And to simplify that, I've prepared these tarballs with binaries, include a makefile which actually takes care of setting up a Raspberry Pi, at least if it's running Raspbian. Now, what I'm doing here is I've got the Raspberry Pi, I've installed a recent Raspbian image, and see, it should be finished by now doing a dist upgrade. Basically, I've extended the file system, I've added my SSH key, I've done a dist upgrade, and that's all I've done on it. And network just works to the point that I can actually access it from the big machine here. Next thing is download those tarballs, at least the binary tarball, on the forum page here, once again, and copy it to the Raspberry Pi, and then I'll show you what to do next while we're at it. Let's take a look. Okay, so here's a login on our Raspberry Pi, and I've already copied these two tarballs there. First one is the sources. We're not going to take a look at that right now. Second one is the binaries, and that one's actually important. Let's take a look. There. What you find in there is a makefile plus 3 subdirectories. The subdirectories only contain binary images for the architectures. That's what we're going to take a look at in the next 3 episodes. But the makefile is actually interesting. And what we could do at this point is just say make and run it. And we could also say time make and see that it still takes an hour and a half to run. But we could also take a bit of a look at it first. Always a good thing to do. First thing you see, BSD copyright, which means I'll leave my name in there with the copyright notice, which I don't really care about with this sort of stuff, because it's just nothing I consider worth much of an intellectual effort or anything. But the important thing is the second part basically says if it blows up in your face, it's your problem, not mine. And that's actually important to me. That's basically the reason why I put things in here. So yes, you're allowed to use this for commercial projects or whatever. I don't care. Just make use of it. Next, we have a couple tunables. First off, you can say, no, I'm not interested with PIC, or not interested with AVR, or not interested with MSP430. Just comment in those lines as you need. Second, by the time you watch this, you might want to adjust the version numbers involved here. They're needed to fetch the source tables and to build the stuff. Then there's some extra packages. I personally use Emacs. I like to have, by the way, if you use VI, fine with me. Whatever makes you happy. I'm sticking with Emacs. I've done software development with Emacs for too long to use anything else. We're going to use makefiles, so having the make documentation around actually makes sense. I more often use the BSD variant of make, which is slightly different. So when I have to use GNU Make on Linux, I just want to have the documentation around. Git should actually be installed already with Raspbian, but I just want to make sure. And if I ever port this to a different Linux or different Unix, it's a good idea to have that in there. And the GCC documentation is also quite helpful. Now, the Atmel AVR and the TI MSP430, actually we use GCC. PIC is a different story, but it helps to have the documentation around when things get a bit more complex. For PIC, we have to build the compiler from source, and the compiler is called SDCC, the Small Device C compiler. And if we don't say no, we don't want that, you can either do a full build, which includes documentation, which takes quite a lot of time, requires a pile of additional packages, because these three we have here have a lot of dependencies. Or you can say, okay, disable pretty much everything other than PIC. Your call. You can control this by setting full SDCC build to whatever makes sense. If you have more specific requirements, you can also use your custom flags by just setting SDCC configure flags. Whatever. If you want to use this on a non-Debian based system, you might want to replace these commands here using yum or package on FreeBSD, whatever. And yeah, that's pretty much all you want to play around with. Here we have the standard packages that need to be installed. It might actually happen on a different distribution or whatever that these packages are named differently. Adjust things as needed. Here we install just the packages needed, and then things get a bit ugly, because this is about the stuff we need for the PIC to implement. There's pk2 command, pickit2 command, which is the programmer software, and then there's the compilers, which is SDCC. We also still need pickit2 command, and the GPASM, which is from the GP utils. This is getting a bit ugly, which is another reason to put it in a makefile. So if you have to build this, or if you want to build this on a different platform, different architecture, this is where you want to take a bit of a look at. And yes, this isn't nice, but it gets the job done. So pretty much all there's left to do is do a time make, or just make, whatever, and let the Raspberry sweat. That's pretty much all there is to it. And don't worry that I'm going through some sort of proxy. That's because of the setup with the additional computer. Last time I tried, it took about an hour and a half. Depends a bit on your network connectivity because it has to download stuff, but round about something like that. So basically means time for a lengthy coffee break or tea break. And other than that, well, once this has worked, we're ready to actually try the hardware. Now, the next couple episodes will be about the development boards I'm going to use to get started. Once again, this trick is to use something off the shelf here to get started, get all the rest to work, and then we can actually replace things here. Because the goal is to get all the blue-red stuff to work and then build other target boards, possibly, one way or another, can be breadboard or whatever, and write the associated code for it. That's what we are really up to, but first we want to get this part to work. And as I said about how to tackle these complex things, we've tried to eliminate, for starters, as many things as possible that were kind of overwhelming. What you want to do is you want to minimize the numbers of possible errors and the probabilities of possible errors at any given time. The more possible error sources there are, the harder the troubleshooting is. So if you know, I'm just touching the programmer hardware, programmer software side because I use an existing board that I know, or rather confident it works, and using a binary image that is reported to work, you can be sure it's either programmer hardware, programmer software. Makes life much, much easier when things go wrong, and things will go wrong. Other thing is use detours. Use one of these development boards even though we'll just get rid of them once everything else works. Makes sense. But by the time we actually start to build our own hardware with microcontrollers, we have come to grips with a lot of stuff and are much more comfortable, much more familiar with things. We have a stack of existing source code scraps that we can reuse, that we know work, and we can focus on building the hardware and writing the associated software, which can already be tricky enough because if something goes wrong, it's still a question, is it a problem with my software or is it a problem with the hardware? Let's see about that later on. Okay, so what I'm going to do right now, I'm going to pretty much not call it a day, I'll just call it end of an episode. I'll edit this stuff up and see how it worked out, and then very quickly see that I record the follow-up sessions where I actually unpack the various stuff I want to use and do 3 episodes on how to get started with those 3 microcontroller families. And then we're going to do a roundup episode where we see how to get things portable. I think. We'll see. Okay, so much for today. Hope you liked it. If you have questions, comments, ideas, requests for, but you need to get us a bit of background on Make or whatever, come to the forum once again at www.stapler-it.com/BIVBlog/37. And otherwise, hopefully, see you again soon. Bye.